Hello and welcome to the Polymath World channel, where we're digging more into space again. And I'm joined today by Peter Swan, who is, at the forefront of much of the space elevator discussion. If you're thinking, I don't know what space elevators are, I've never heard of them, well, this is a great episode for you. It's a really fascinating concept, and I'm delighted to be joined by you today, sir. Thank you for taking the time to speak with me.
I'm looking forward to this. It should be enlightening for me as well.
Yeah. I first met you at the British Interplanetary Society conference last year, where you were presenting about the Space Elevator Consortium and the whole concept. And I thought it was incredibly innovative. It was something that I'd only heard loosely in passing and only really knew of in a more of a sort of a science fiction context. But this was really groundbreaking, and I'm really excited to dig into it. So the floor is yours to take this as you like. But talk us through space elevators and your role in this innovative program.
I'll talk about the background of the role, and then we can share charts. Basically, the British Interplanetary enables us to talk about what can be real. It started in their early days with Arthur C. Clarke, and it's gone since then. I met Arthur C. Clarke in a BIS meeting down in Brighton one time and really
Wow.
enjoyed the conversation. And I mentioned I was in space elevators, and he sketched one out and gave it to me in a napkin. Now, if I could find that napkin, it'd probably be worth something.
Would
But
really
I
would.
don't know where the napkin went. It went someplace, but it was an enjoyment of sharing ideas with somebody who was far senior in all kinds of ways. But it was fun. And so the delight of sharing new ideas and pushing the envelope in capability is one of my strengths. I've been doing that from the beginning. I've always been in the R&D, research and development end, way out in front. People laugh a lot, but it's a fun part of engineering and development. And in the past, I've had two mega projects. We call them mega projects if they're greater than $1 billion in 10 years. And both of those were successful. So I feel right at home in space elevators. It'll be more than 1 billion, and it'll be more than 10 years, more like maybe 20 billion in 20 years, but something like that. And it's fun being out in front. So let me share my charts here real quick, and then we can start off and go from there. Let's see, that would be that one right there, I would believe. Yeah, let's do that. Okay, can you see that?
Yes, I can.
Okay, just a little background on my part. I said I've been in the front end, and as you look through there, there are a lot of activities that I've been involved in many different organizations. But the fun part is I'm talking to the people out in front around the world. And we talk about all kinds of things. The image on the right's from the Heinlein Association. Of course, they're science fiction, but the leader of that pushes for taking science fiction and making it real. So they've supported me a lot. And the International Astronautical, the Academy of Astronautics is another one of those international front end in space arenas. So I like to work with people who are exciting, have great knowledge, and have an open mind about the future. I don't mind questions, and you'll come up with questions, and I can be reached at the email at the bottom of that page, and I'll send you the charts after it's all over so you can put them wherever you want. But
Thank
the real kicker is there's a lot of future out there, especially going into space. The way I like to look at space today is we're in a great transformation. We're going from everything run by governments to a significant portion of the business being commercial. We've got Jeff Bezos, we've got Elon Musk, we've got billionaires from other parts of the world. The commercial world tried to land two spacecraft on the moon. Now they had little anomalies here and there, but man, when we started, we had a lot of anomalies. So, that's
you.
just a part of the world that is exciting right now. We are going off planet. We're going to go with robotics first, and then we'll go with people, and it will be expanding society and the civilization remarkably. Now, I'm not saying it's tomorrow, but we all look out in the future when we're looking at these things, and it's really neat. And the key is that the space elevator will enable this. We're hoping that it would be a commercial program, just like a transportation infrastructure, railroads, bridges, things like that. And so what we want to do is build a commercial entity that would go and build space elevators and open up the future for us. So
Mm.
I'm going to just jump into a few charts here at the beginning. Just, got to figure out how to go forward here. Usually it's just I hit a button there. That's interesting.
You got
This
the
is,
arrows at the bottom.
yeah, that's what I'm hitting now. What? Okay, this meeting is being recorded. You're sharing screen. Boy, that's interesting. That's all good. Let's see. Oh, there's arrows down there. There we go. We use these arrows.
Mhm.
Okay. Okay, so let's start off with what is a space elevator. We want the space elevator to be in parallel with advanced rockets. I call it the combination in an association where we go forward and we use rockets where it's important, and we use space elevators when we want to lift mass up to geosynchronous and beyond. Rockets are great in low Earth orbit, and they're great at moving people through radiation belts fast. Those are really two characteristics that are important. So we want to be a dual space access type project. Now, I just came up with a favorite number about, I guess, 3 months ago, and I love it, and we'll talk about it once in a while. But if you have a space elevator that raises everything with electricity, okay, we raise 70% of the mass on the pad to geosynchronous and beyond. We toss it out to orbits around the moon and Mars, but we take 70%. So our delivery efficiency is 70. If you think about rocket equation, they get only 2% of the mass on the pad to low Earth orbit.
Yeah.
Now, having reusability and a lot more launches, so the cost is coming down, and that's very good. Delivery efficiency does not improve.
Mm.
As an example, for Apollo 11, we put 1/2 of 1% of the mass that was on the pad at Cape Canaveral on the moon.
Mm.
And we threw everything else away. And that's the same way Artemis is going forward, with the Europeans helping them and everything else. We've got a problem. It's called the rocket equation. It's been around for 140 years or so, and it's really lousy for delivery efficiency. So the space elevator can lift 70%, and that's a remarkable number.
Yeah.
Okay, and by the way, we just started realizing the impact of that. I mean, we've been working space elevators since 2000 with Dr. Edwards, essentially as real potential since 2000. And nobody's ever really articulated that. And I found that number about, I guess, 2 months ago, and that's my favorite number. Okay,
It's,
how's it work?
it's
You've
really
got,
incredible.
yes, go ahead.
I was just saying, it's staggering. It's the thing that really jumped out to me when you did your presentation back in November. That level of efficiency is so disruptive.
You know, if you think FedEx or Amazon delivery, would they take a job like that? And, if they're going for commercial, they would not, so that's why it's a commercial venture. We think it could be very easily Amazon or FedEx or a bridge builder or somebody like that doing it instead of a government. Okay, the way it works is you have a long tether, 100,000 kilometers long. By the way, that's not the only number. We can use all kinds of numbers, but 100,000, like a nice neutral point, it has enough length so that as it spins around your belly on the lower left, Larry Bartosik is a friend of mine. He did this cartoon. If you spin it around your body, the centrifugal force pulls the rock out, and the string is taut. And that's the way it works on space elevators. You've got a Earth, and it's spinning, and you've got a large mass at the end called the apex anchor. And as it goes around, it puts tension in the line. And you put the tension so it's strong enough. I mean, it's enough so that the tether doesn't fall down. It stays there forever. So then you have a tether climber, and you use electricity to climb. We just did a tether climber study in the International Space Elevator Consortium, and we showed that today's material, we could lift a 10-ton payload with a 20-ton carrier with today's material. and today's motors and today's electricity and all that kind of stuff. So we show we can do it engineering wise. So we're looking for 70% of the payload being the mass being payload, but that would require lighter material and stronger. Oh, we've got that now with the new two-dimensional materials. We'll talk about that in a few minutes here.
Okay.
But just in perspective, so everybody understands how big this is. If you look at the lower right, we show the magnetic fields, and 100,000 kilometers goes outside the bow shock. I mean, we've got remarkable length. Look at a small Earth compared to 100,000 kilometers. So it's a large endeavor, mega project for sure. So the vision is simple. We want to be the green road to space, okay? It's like putting a bridge across a river and you use all those little tugboats down in the river, whereas you just drive a car across at 70 miles an hour.
Mm.
So it's like a bridge going across a chasm, and we do the same thing. We take a bridge and go vertical. So as I mentioned before, our approach is a dual space access architecture with rockets. We don't want to be our only self. We're going to need rockets also. Now, we came up with the term modern day elevator when we recognized that we do have the material for the space elevator tether. In the time of 2000, 2010, we had 2 or 3 ideas, but nobody confirmed we had the material. So it was still science fiction in those days. We have the material today, and I'll have a chart on that later, but it's a super graphene laminate. And in Korea, they've run out the graphene, not the super graphene laminate, but graphene to 1,000 meters, 1/3 of a meter wide. They actually produced it in South Korea. So here are the characteristics that go with the term modern day. We're ready to enter the engineering phase where we start doing big testing. We've done enough research projects that we're ready to start engineering. All we need is a little bit of funding money here and there. We're the green road to space because we don't leave any trash behind them as we raise up on electricity, and we don't burn rocket fuel in the atmosphere. So
Yeah.
we're the green road to space. Uh, we want to join those things, and we are very efficient and move massive cargo. I'm going to give you some numbers later that really blow your socks off, like 30,000 tons per year if we have our setup of 6 space elevators, initial operational capability. We've only put up 22,000 between 1957 and 2022. So we put up more in a year than the humanities put up so far. I mean, those are numbers that just blow you away, and you start thinking, holy Toledo, how does that work?
Mm.
And so we're really out there. Now, just to show you what we're talking about on the material, we have a quote that was from one of our big studies. It says, the manufacture of telequality material for space elevators still needs to be more development, of course, but we're on a trajectory to have it ready for us in 5 to 10 years. The material, and of course, it's a brand new material that's like 150 times stronger than anything we have today, and it's like 10 to 20 times lighter than anything we have today. So the material will change manufacturing in the future. And
Yeah.
we have,
Would you mind if we just talk? Would you mind if we just talk about graphene for a second?
sure. By
Because
the way, much of it is being done at the University of Manchester where you went. So
yeah,
you're right
and
to
at
do it.
Cambridge as well. I know people who've been
Yes.
working to industrialize it. For those that don't know materials science, graphene is the super material everyone's been waiting for. Super light, super durable, super conductive. And yet, when people think of graphene, they think of a graphene pencil, maybe sort of a. It's not something too unfamiliar, and yet it has been difficult to industrialize. Um,
Yes.
so in terms of getting hold of enough for 100,000 kilometers, how wide did you say it was?
The one that was produced in South Korea was like 1/3 of a meter wide.
Third of a meter. That's the one. Yeah.
But we need 1 meter. We need 1 meter, but that's just the size of the
Yeah.
manufacturing equipment. That's all that is. Now, it turns out you can catch up real fast on this graphene by going to our newsletter. at our website, down at the bottom of the page there. Go to the newsletter. In there, we have a graphene report every month. It's basically one or two 8.5 by 11 sheets of paper, and full of data. And it's in our newsletter every month. So if you go to the last 20 or 25 newsletters, you can go from the beginning to where we are now and catch up on where graphene is today.
Mm,
And Adrian Nixon is our publisher of that, and he's right in the middle of it.
right.
And so you can really catch up by just going to the graphene page also on our website, and you can learn what you need to do, and then from there he's got references if you're interested in pursuing the polycrystalline graphene or the superlaminate graphene. It really is remarkable. I mean,
Oh, it's the biggest game changer in material science for a very long time. Could change the world. I'm just wondering if it's developing enough to where
yes.
maybe this could be one of the biggest obstacles.
No, no, it's developing enough. You can tell because there are patents coming out,
Mm,
stuff like that. So, so yes, it's coming out very rapidly. And we just had on the last newsletter, either that or the one before, I've forgotten which one. No, I think it's his last one that I just read. The newsletter came out like 2 days ago. They showed how, the graphene is two-dimensional. So you only have XY, and it's one atom thick. And so we've always thought we'd have a bunch of layers, like, 10,000 layers
yeah.
for one accelerator tether. The the concern that we've had is the slippage between the layers. Now,
Hmm.
we showed, I wasn't involved. It was just shown that we can do north-south. So we can go in the third direction and bond atom to atom. So you have the same strength north-south as you have XY. And so it really becomes more than just two-dimensional because you bond the atoms north-south. They've been using lasers and they've been using high pressure. And you can force the carbon atoms to bond north-south as well as east-west. And so literally we can stop the slippage. And another aspect of that article was graphene is very, very slippery. So if we're going to try to climb on graphene, we're in a little bit of a problem. We got to figure that out. But if you put hexagon boron nitride, which is another one of these two-dimensional materials that they're working on very rapidly, it's lagging graphene by probably a year. You have the hexagon boron nitride, which has like a 0.2 coefficient of friction. If you put those on the outside 30 layers, maybe pick a number, I don't know, and you bond those to the carbon below them, then you have no slippage and you have great friction for the wheels to turn on. So
Mm.
the two-dimensional material progress is going very, very rapidly, and we have it in our newsletter as an easy way to get up to speed on it. So it is remarkable, though. You're right. It's going to transform material science.
Okay.
Oh, yeah,
Well,
that's just a pretty picture that Adrian Nixon came up with. I always like that one. Okay, the concept. We have benefits from this new transformational capability. If you think bridge, these are all natural to you. You say, "Whoa, why didn't we think about this before?" But it's daily, routine, safe, inexpensive, and very, very little environmental impact. Because we're using carbon right now, and if we use carbon, we take it out of the atmosphere. We do good for green. But anyway, minor anomaly there. So 70% I've talked about. It's the green road I've talked about. Here's the thing about space elevators. We're talking about daily routine. Our planning is one per day, 20 metric ton climber, and we have 6 space elevators in 2 pairs. I mean, pairs of 2. So you have a galactic harbor, each one of the pairs. And so they have one up, one down, 2 up for commercial, or one backup. So the idea is you have 2 space elevators in the galactic harbor. I'll have a few pictures along the way. But you do really large movement of mass. The IOC would be 30,000 per year. I mentioned that before, but the full capability would be 170 tons per year. Now, if you just remember that a little bit, when we get to the users down on the right, I'm going to show you a chart of projected needs from customers. And rockets can't cut it for some of those. We have to have something. One I wanted to mention, just fun little result, is we did a study with Arizona State University, and they did a bunch of students doing the orbits, the calculations of the orbits between Earth and Mars. So Earth and Mars rotate around. So we wait 26 months so rockets have the shortest, easiest way. And
Yeah.
then we send the flotilla up to Mars. And so we have 26 months, don't launch to Mars. Well, since we have so much velocity at 100,000 kilometers, we can launch every day to Mars. Every day. Now, the fastest trip is 61 days. The students came up, were really proud. They came up with this ellipse that got them there at 6. Now, you do have to have a rocket to slow down because you're really hauling.
Yeah.
Okay, but the point is you can go every day. So if you want to send pizza, you send it on the 61 days. Now, some of the trips are longer, like an average of 140 days, but they have some that go by Venus. They just miss the alignment, so you got to go by Venus. That might be 400 days. But send hammers and nails, and you don't have a time need for hammers and nails. So, but the point is, we can launch every day toward Mars versus rockets every 26 months. So, I mean, the space elevator has hidden little characteristics that are pretty neat. Okay, here's the way we thought of space elevators in the future. Of course, would be driven by the commercial investors. If they see a big market, they'll do a lot of them. If they see a modest market, they'll see this way, or maybe a government will have one of them. But galactic harbors are a logical extension. This is what I talked about going to Mars: fastest transit, daily releases, massive cargo. I mean, what more do you need? Oh, another characteristic of space elevators, at the apex anchor, you can assemble things. So you take up 14-ton payloads at the beginning and you put them together. So you have a 14-ton rocket motor, you have a 28-ton spacecraft, and then you have some guidance comms and another 14 tons. 4 components assembled at the top of the gravity well at the apex anchor, and you release it to go to Neptune. We're already going really fast, and we can get to Neptune in like 2 or 3 years with the new rocket and gravity assist, of course. And then you get to Neptune and you could come home with your rocket. So literally, by going up and assembling at the top of the gravity well, we could return stuff from planets. I mean, there are so many inherent little neat pluses that we don't talk about it in the past. Here's our students from Arizona State University who came up with a bus schedule to go to Mars. I mean, think about that a minute. We have a bus schedule. I mean, most rockets can't launch on time. Now, Mr. Musk is doing a good job on that, but most rockets, they launch when they're ready and not when there's a schedule. So this is really a neat little concept. Okay, we got to move faster. Well, if we go all the way out to 163,000 kilometers, just build it longer. Okay, the material will take it, so no sweat. You can leave the solar system with no rockets. And you get there in like a third of the time for the Voyagers. I mean, it's remarkable the velocity you get on these things and the mass that you can bring up, 170,000 tons. I mean, that's really remarkable. And then assembly at the gravity well, this is a pretty little picture where you bring stuff up, you assemble it up there. Oh, by the way, besides assemble, you could store, you could release, you could capture, you could repair, you could refuel. I mean, you could do all these things at the top of the space elevator that we can't do in space, really. And of course, I've said the Green Road, and I've got that little Apollo example down on the left. By the way, I loved Apollo. I watched Apollo 11 at some ridiculous hour in the night in Denver, Colorado. But anyway, we all have stories about that stuff. So the real question is, why are we waiting for space elevators? It's really stupid. They're the best thing that ever's come up. So we're out there trying to figure out how to start the space elevator program. And there's 2 companies that have been formed. My wife and I formed one called the Space Elevator Development Corporation. And then there's a Space Railway Corporation that's also being formed. Okay, I was going to mention humanity's needs out there. I've got the historic ones, geosynchronous satellites. We could just take those up every day. That'd be no sweat. And we can assemble them at an apex anchor, so there's no longer any restrictions to the fairing and stuff like that. And then we have future. Like space solar power is big on everybody's topic. I don't
Mm.
know if you've covered it yet in your show.
No, I haven't, but I'm very familiar with it. Yeah.
I recommend the UK is leading that, by the way, and it would be a good show to have
Mm.
Martin Soltau or Ian Cash, the designer of the spacecraft that they're thinking about, stuff like. I mean, you've got the experts right there.
Mm.
Okay, space solar power. Essentially, in the old days, we were talking 5 million tons to geo. It's down to about 3 million now to do what we need to do for humanity to provide electricity south of the border. Well, also to England and a few other places. But we need to provide commercial energy. That's why I think space solar power ought to be a commercial program.
Mm.
By the way, the other thing is those satellites, the minimum size, the one the UK is designing, the minimum size is 2,600 tons. Now, I haven't done the numbers, but I would wager to say nobody has put in the total human things, we haven't put 2,600 tons to geo. And
Mm.
this is just one satellite. And the UK wants to do 5 to cover the UK. So that's 13 million tons to geo. Now, wait a minute. Now, I don't want to do the math because I can't do it at this point. But if that's only 2% of the mass on the pad, I mean that's hilarious.
Yeah.
Sad.
Never gonna
Anyway,
happen.
so doing it by rockets is problematic. Mars settlements. Mr. Musk has stated he wants 1 million tons. I mean that's a lot of mass, and then he's got to have people in his rockets. So the rockets get about 1% to the orbit of Mars. 1% of what they take off with. So do the math there.
Mm.
Moon Village. Now, Earth sunshades, that's a big one they're talking about in limited circles. But if we're really getting in trouble with temperature on the Earth, about the only way to solve that is to put a shade between here and there. And they've got designs for it. But, but, but that's 20 million tons beyond geo. So if you're going to do that at 1% delivery, I mean, that's toast. So you almost have to have our, 70% number there. L5. I'll tell you, I went and did the research on L5. Took me 6 months to get them to admit there was a number that was out there on how big it was and what the mass was. They never wrote that down. When I go to conferences, I'm kind of obnoxious because when people come up with ideas, I ask them how much does it weigh? And they all go be smart people and say it weighs zero out there. No, no, no. How much it weigh on the pad? And the L5 Society, and that turned into the National Space Society. They want to put 20 million tons out to the altitude of the moon. So, as you can see, our future of humanity moving off planet really needs an efficient manner to do it. And I'm proposing one. There are other ways, but anyway. So, what do we want to do? Well, the dreams are pretty big. We want to do all these things. Now, here's a little aside. At the which one was it? The Paris IAC, International Astronautical Congress. Mr. Bezos and his team put that blue lander at the site. But they had little ropes around it and guards, to make sure nobody stole any part of it or anything. Well, I walked by late at night one time and nobody was around. So I kind of went inside the rope and touched it. I touched the blue lander. Of course, it's just a prototype. It's not to be the one to do. But Mr. Bezos has a spectacular idea on how to get mass to the surface of the moon. But it takes a big rocket to do that. And here's new vision by the National Space Society. Let's go live off planet. Whoops. How many tons is that? And of course, lunar lander. This is a funny story where Mr. Musk is going to land and deposit stuff. And so if you look at this Starship, it's huge, and it could take a lot of people, a lot of resources. So NASA did the correct thing by hiring them, but they've also hired Mr. Bezos now also. So they have 2 landers. And let's go to Mars. Everybody forgets that it takes 5 launches to get one space starship to Mars.
Mm.
It's not one. It takes 5 launches to get enough fuel up there and people up there and supplies up there. Then I just kind of summarized that. Looks like the same chart. Oh, well. Oh, I know what I'm doing. I'm going backwards because I'm hitting the wrong button. No, no, maybe I duplicated charts. Oh, anyway, so here's a little summary of where the customer is. And you
Mm,
look at those numbers and you just say, "Whoops."
mm,
Do that with rockets. Okay, just so for background, if anybody wants to really learn about the modern day space elevator, where we are, where we're going, graphene, design of the different parts, stuff like that, we have an excellent set of 11 articles, papers in the British Interplanetary magazines from the summer of 23. The JBIS and the space flight had a little competition for articles. So we ended up writing a bunch of articles. It turns out now you can get to them free of charge, and they allowed us to do this. We put those pictures on the web too. If you download them from our site, the isic.org chart, you can get all 11 of those articles. And they define space, the modern day space elevator. And so it really helps to understand. It's got the right stuff up there talking about the material, talks about your galactic harbor commercial venture, cooperation, competition about, how we can do it best with rockets and other things, modern day definition and incredible engineering by the Japanese. So that's a really neat little pair of magazines you can get uh, to understand. And then recently, it was November issues 94, which they just published a little while ago, the JBIS, and there's an article in there called The Modern Day Space Elevator's Evolutionary Growth. That's talking about evolutionary for the elevator, but
mm.
the revolutionary concept of the apex anchor. We always thought the apex anchor was was a counterweight. That's good. We take care of that. In reality, we fix a apex anchor up there and we can build things. And we talked about 11 missions, planetary defense, communications, navigation. We're a stationary thing rotating with the Earth, but stationary. So navigation would be pretty easy and you could do comms for any place. So there are 11 missions up there at that place. Yeah, I keep hitting the wrong button. Sorry. Um, and I'm sorry. I was thinking differently. Then there are two reports from the International Academy of Astronautics. Now, what you want to think about here is that's about 1,200 rocket scientists. Nobody in there, is named a space elevator guy except for me and some of the writers here. But we had 40 rocket scientists write these, and the conclusions were the space elevators are feasible. And then the second one we did in 2019 is here's the road to a space elevator era. And so those were done by rocket scientists. I love that. They were comparing us to rockets. If you go to the body of knowledge of space elevators, that's our website. We've got like 16 study reports, research reports. We've got the IAA books we just showed you there, and then we have the videos at YouTube. So we really have a lot of knowledge there. So, transforming the future is what we're after.
Mm.
Why don't we stop here and see if you've got any questions or anything about
Yeah.
it? We can get into how you build space elevators and the material strength. I've got those and stuff like that. So
Well,
you got
yeah,
it.
I have my own questions, and I have questions that just general layman may have. Um, so let's start with the technology. You have your harbor at the bottom, floating on the sea, with the graphene cable going all the way up, hopefully to 100,000 kilometers, with the anchor at the top, and then your space elevator going up and down that can take 70% of payload all the way up. So technologically, it's the graphene cable that is accelerating and in development, but is there anything else that's not there yet in terms of technological capability?
Okay, as a person who's put satellites in space for over 56 years, and I had like 92 Iridium satellites put up there. The boat at the bottom, we're going to put it in the middle of the ocean so that it gets away from any legal issues of land mass. We want to have it on the equator so we can get rid of 80 to 90% of all weather. And there are places west of the Galapagos, about 2,000, 3,000 kilometers, that haven't seen a lightning strike in 100 years. And hurricanes don't hit equators because they go north-south. No winds, no real storms or anything else because there's no land to raise the air as it flows over and stuff like that. So we'll have a floating platform anchored to the sea bottom, of course, but it'll be mobile, so we can move the tether. So that we could put a sinusoidal wave on the tether, so we can move out of the way of big debris. So the ocean platform is they make them all the time. They're called oil derricks. And then we have the climber, and that's a mechanical device. It goes up and down, and it's unique that it's climbing by wheels. But wait a minute, we do that a lot on cable cars and a whole bunch of other
Yeah.
stuff. So, and the elevators have a special characteristic also. So, I believe those could be built. You put enough money in it, you can do those. Then you have the apex anchor, and we had a student. We have a student intern every year. You can apply for that if anybody's listening. And she was a student in Edinburgh in astrophysics. And so she was our student. And the question I asked her to study was, how do we get mass for the apex anchor? Because we have to have a certain mass to hold up the tether. So she had all kinds of stuff. But the bottom line is we want to go get all the dead satellites at geosynchronous
Mm.
and buy them from the owners because the owners still own them. But it ought to be a cheap sale because they don't want to be responsible for running into anything and killing anything else. So, because that's their responsibility. So, if we gather those in a big net and take that up, we'll increase the mass. So, we have a pretty good idea of how to build the counterweight. And then the question is, how do you build the apex anchor to do refueling and repair and storage and stuff? And that's just a space station. We've done that. How many countries have space stations? I mean, the Indians are about to launch one. So the only real question is the graphene. You're correct. And the graphene is going so fast that our researchers came up with that quote that it'll be ready between 5 and 10 years for the space elevator tether, not just, for commercial use, but for our purpose. And so there are people at the GEEC, the Graphene Engineering Innovation Center at Manchester, working that as a side job. That's not a principal thing. And we need some money to start looking at how do we develop the tether. And I call it the tether segment because we got to have reels on both ends. We've got to have a simulation that provides the knowledge of every location along the tether. So it's a tether segment that we have to work on, not just the tether material. So, when you're developing a major project or mega project, you define it by segments. So we have the earth port segment, the tether segment, the tether climber segment, and the apex anchor segment. And then we have an ancillary command and control segment that would go either in the floating platform or someplace else with good comms. So we have 5 segments we have to develop. So that's where we are in the concept development, the architecture of the system.
That's tremendously exciting. My next question is, you've said it's powered by electricity, but how is it powered? Are we talking solar here? Or what kind of generation?
Yes. we, we have a study ongoing actually right now. And the question is, how do we power the tether climber? And so they're looking at simple one, solar cells. That means you got to have a lot of solar cells, a little heavy. We're looking at lasers. There's a lot of technology going on in lasers for different things. And then we've got the cabling. Can we capture electricity from the electromagnetic fields and power the cable, or can we run power from the ground up? Here's a little departure from the question, but when you're doing mega projects, it's logical to break them into sections, not segments, but sections. And what we have is the Earth atmosphere and the planetary near range effects. So what we need to do is we look at the threats to a space elevator, winds, lightning, stuff like that. Now that's no different than what the launch guys do. They do the same thing. So we would want to look at the winds at the equator, which are not as great as any place else. We'd look at the lightning. Well, there hadn't been a lightning strike in 200 years, but 100 years. But of course, you got to plan for it. You can't just say no. And then we've got to work on, angles of the sun and daylight, nighttime, and all that. So as we go through all those questions, we'd have probably a different design for the lower portion than we have above there. And then when we get above the atmosphere and everything, we call what I call a space debris arena. We've got a whole section on space debris if we want to go into that. We have the space debris area, and then above that, you're going to be where the gravitational forces are less. So maybe your tethered climber can use a power source less powerful than what you needed to get off the ground.
Hmm.
So what we're doing is segmenting. I keep using these different words. We're differentiating by altitude the requirements to the space elevator tether and the tethered climbers. And so it would not surprise me. Now, this is not in the plan. We haven't gotten to that point yet. It would not surprise me if we had a base station above the atmosphere, but not too high. And so it's not in orbit in any sense. It's just on the tether. Nothing is in orbit on a tether. Okay. That's first rule that people get confused with. They try to relate orbital velocities to the tether altitude. Not true. Only one place is it equal, and that's a geosynchronous. So above the atmosphere, we could have a space station. So we could have cable cars going up and down with rotating tethers, at the bottom for the energy. Then when you get above the atmosphere, you still got a lot of gravity. So maybe you use something from there, lasers from the ground. But when you get to one radius from the Earth, okay, 1/r², get one radius of the Earth, your gravitational pull is 1/4. So maybe we use space solar power from there. So the complexity of operations is being looked at right now with our study on how are we going to power it and stuff like that. So, you've got all kinds of options there that we have to assess, and we're looking at them all, trying
Hmm.
to understand. We don't have any answers right now. We've got proposed answers, but, nothing that we pick. And everybody wants, just like you want an answer right now for everything. And as the chief architect for this organization, my statement is we can't define the details of the space elevator now until we do two things: is do an architectural study about all the requirements at the whole at the space elevator from the ocean all the way to the top. And we've got to look at all the requirements. By the way, some of those requirements are customer requirements. So we have to look at customer requirements as well.
Yeah.
Because one of the things that's obvious is that geosynchronous, it's a beautiful location. We climb to geosynchronous and we release the payload and it sits there
Hmm.
because it's going the same speed as geosynchronous. Do you want that, or do you want a space station up there? Do you want a place where you can assemble, refuel, repair, store, all this kind of stuff at geosynchronous? And the answer is tending more and more toward, yeah, we want one of those. So what we need to do is figure out how we're going to have transit stuff that's going up the apex anchor, go through a space station, et cetera, et cetera, et cetera.
Yes.
So there are a lot of customer requirements. Like if the customer says, I have to have refueling at geosynchronous, I mean, then we got to put a gas station up there. And, so customer requirements are big at this point. We have not defined the customer requirements very much. We've hypothesized that we need 20-ton payloads. 14-ton payloads initially and 79-ton payloads at full operational capability. But those are hypotheses. And one of my friends says, no, tether climber has to be 500 tons. You know what I'm saying? Okay, have some patience. Let us put the preliminary ones up and make them operational, get refunding, and then we could do 2 or 3 parallel ones and make a 500-ton. So customers are important. We have to figure out what they need, and we have not done that in a rigorous manner.
Hmm.
We've talked to people and gotten feedback, so that's where those numbers came from in the 3 million tons and stuff like that. But we haven't had a rigorous request for inputs from customers.
Hmm. Well, the good thing is, obviously, there are a lot of viable solutions. This isn't a roadblock. This is there are a lot of viable solutions. I wonder, where have you got the most interest in this from?
The The space solar power community knows they need mass to geosynchronous.
Mm,
Some are reluctant to stand up and say, I have to have space elevators, because then they might be tagged by the sponsor to pay for the space elevator development.
mm,
So they're hesitant of saying we've got to have space elevators.
mm,
But they are in the process of looking at our stuff. And I go to the meetings of space solar power. I go to, you know, satellites and communications at geo stuff. And I go where they are. I'm working with the lunar, what is it? The Moon Society. I work with those guys, and they keep talking about how they need mass, but they won't define it. And then there's the sunshade out there between us and the sun. I've worked with those guys up at the University of Colorado in Boulder and stuff like that. So I'm in the orbits of, so to speak, of customers,
mm,
and I talk to them and I present stuff. And well, our next step, I think, is come up with a memorandum of understanding between us and them, saying we need space elevators. We need to have a few people stand up and say that. And so that's where we're at right now, trying to develop that MOU. No cost at all. But, we need to stand up and say it would really be hard to do my mission with rockets.
mm.
We might destroy the atmosphere. We might, blow up a bunch of times. Let's let's think seriously about space elevators. That's where I'm trying to go right now, is how do we get people to sign up and say the community needs space elevators for the following reasons. And you don't even have to list them. Just say the community needs space elevators and sign it, type thing.
Yeah. And why not someone like Bezos or Musk or sort of the super companies, given the incredible payload opportunities? And with that, yeah, how much do you think the total cost of this would be? I mean, it's a difficult question, I know, but
I estimate, okay, now I've done two mega projects, so I have some background. I've come up with 20 million, $20 billion. Now, the early estimate back in 2004 or so was, um, 2012 was 7 to 8 billion, but it's gone up since then. So I think 20 billion is probably right. Now, 20 billion is nothing if you wanted to build a bridge or a railroad or someplace significant. It's almost nothing. So what I want to do is I really want, like and I'm just naming these off the top of my head, Gulf Oil, Texaco, the gasoline people. We should call them energy people. And we should call, the North Sea guys up there doing energy supplies to England. The 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 energy from the underground is going to run out someplace. Why don't you jump in and become a leader in energy from space and do
uh,
space solar power? And if you do that, then you need to build a space elevator. Or if I want to be an adventuresome and go to Mars, maybe I ought to put money in a backup plan called the space elevator. So those type of things. I'm about to, let me rephrase that. There's a large need to go talk to Mr. Musk and Mr. Bezos and some other people like that. And I'm in the process of trying to figure out how to do that.
mm. We
It's not trivial to walk in and say, I need money.
no, no,
You need
I'm sure.
credibility, and you need an avenue with somebody standing up in the organization saying you ought to listen to this. So yeah, if you've got any good ideas, let me know.
Yeah, I wish I had a phone number I could just throw you away, but
Yeah, that'd be good. Yeah.
I have so many more questions, and perhaps we should do a second episode sometime. But for people, particularly young people who are getting into engineering and aerospace and physics and those sorts of things, where can they go to find out more about this? Where's the best place to look? And with that, what would you recommend is the best route into this?
Well, yeah, the body of knowledge is at www.isaac.org. We've got 800 citations for all the documents you need to. If you become a member of ISIC, and for students, it's almost nothing. And for us real people, it's almost nothing, plus maybe double almost nothing. It's really insignificant. You get an avenue to a source of documents that can only be given out. We can't put it on the web and have it global, like professional papers in magazines and professional papers at conferences. You're allowed to share those with your contemporaries in your company and stuff like that. So we've got documents in Zotoro, which is a document storage arena. So if you're really interested in doing research, like for a PhD program or something like that, man, we've got the documentation for you. The web has a lot of good information, but it's almost all dated. I was just commenting on a 2023 study by a very knowledgeable person. I don't want to go into details, but it very, very knowledgeable in a responsible position in the space arena. And he quoted everything from 2019 before. And as I mentioned earlier, the modern day space elevator is only like 3 or 4 years old, the term modern day, which reflects that we have the tether. And so all that stuff that's been done in 23 with those 11 papers of the British Interplanetary, all the talks at the International Academy of Astronautics or the International Astronautical Federation Congress. The IAC is a global organization that has space focus. And they have 6,000 or 11,000 attendees. In Paris, it was 11,000. And in Sydney, it's going to be about 11 or 12,000 attendees, all professional space. And they give papers, and it's like 5,000 papers. And so we get about 20 papers a year for space elevators. And we put them on our website, by the way. And so we have global inputs from all over the world on space elevators. China, Japan, uh, uh, Romania, Spain, all over the place are talking about space elevators. The documents are at our body of knowledge at isic.org. So if you're interested in space elevators, current, you have to go there. It's not out there on the real web. They just don't cover it. They keep going to Wikipedia, and I think Wikipedia's last entry was, like 18 or 19. They haven't put anything out there lately. They don't have the British Interplanetary 11 articles. And, if they don't have that, they're not up to speed.
Hmm. Yeah, and with
So,
that, people should check out the huge number of space conferences that happen throughout the year, all over the world, a lot of which you can join online. You don't have to be there in person to hear about more
right.
of this research. I have a lot of questions about the commercial side, the safety side, and as well just opening up all the possibilities beyond the amazingly disruptive things you've mentioned here today. So perhaps we should have another chat as well sometime. But in the meantime, Peter Swan, thank you so much for joining us today on the Polymath World Channel to tell us more about this really innovative, amazing, and really disruptive project that you're working on.
Well, I'm really enjoying it. I've always believed that when you finish your work that you've been doing for your career, that's just a graduation to the next phase.
Yeah.
The next phase, you want to have some passion. You go for it. Golf's one of my passions, so it's out there. But my passion is to take us further into that step, beyond Earth. And I see this as the only way to really be economical and efficient and all the rest of that stuff. So I'm fighting an uphill battle, but it's such a neat passion, and I keep pushing it, and it's fun. So anytime you need me to help you, just let me know. We'll go from there.
Well, that was another thing that struck me when I met you at the British Interplanetary Society. You were talking to myself and a lot of the younger people, asking us questions, interested in who we were, what we were researching on, what our passions were, and you struck me very much as someone who was really passionate about investing in the future of space and in the next generation. So, I want to thank you for that as well.
Okay. Well, you're welcome. I love it. It's easy.
Thank you, very much appreciated.
Okay, well, thank you very much. I've enjoyed this, and I look forward to our next opportunity.
Thank you so much for watching. Don't forget to like and subscribe. Stay tuned for more amazing conversations with incredible researchers who are changing the world we live in and driving humanity forward. Feel free to check out my Instagram at polymath_Sam or go to my website at www.sam-mckee.co.uk.